Okay, so then, okay, I will go to the second part of this talk, which is looking at this ion imaging method. Up until now, all I've talked about are lead isotopes. Now, of course, what we'd like to be able to do sometimes is do a full uranium-lead analysis. Now, that's a little bit trickier. To go back to how we typically do a uranium-lead analysis by SIMS and a zircon, if we start with a series of standards, so these are the blue dots here, and we make multiple analyses of our standards, and we use this to define a calibration curve in lead-uranium ratio against something like UOU or UO2U. So this is our basic calibration curve. If we then measure a spot, this yellow point here, in an unknown zircon of unknown age, what we can then do is look at where it falls on the calibration curve at the same uranium oxide uranium ratio, and then we look at the relative difference in lead uranium. And of course, these are done in a standard, so we know the lead uranium for the standard. So we can get the lead uranium for the unknown, and we can get the age. That's relatively simple. Now, this curve relies on an awful lot of different factors: spot size, beam density, sample chamber pressure, secondary ion energy. I'm not sure anybody understands it all. It's very empirical. But if we go to scanning ion image and we start selecting areas from our image, we're going to need a calibration curve for each of those areas, because there's no guarantee that if you take a, say, 100 by 100 raster, there's no guarantee that the relative ion yield for lead and uranium in one corner of that area is going to be the same as in the center of the area or the side of the area. And in fact, we know it isn't. We've tested that. So what we can do is, if we now consider that this analysis, this yellow analysis, is actually an area that we have defined within our image area here, an area that we want to know the age of, then we define this area here, and then we analyze a lot of different standards, again using the ion image method. So each ion image will generate a point on this curve for a given region of interest. So we might have 6 or 7 or 8 standard measurements done as ion images. And when we select this particular ROI1 here, then we need to select the same ROI in each of the standard images to generate a curve. And this curve is basically a ROI-specific calibration curve. Now, I won't pretend this is easy. It's incredibly tedious because it really increases the amount of work you have to do. It's okay for one ROI, but imagine you have put, as somebody did recently, about 50 ROIs on here, and I think it took her about a week to process the data. But it can be done. And here's an example of where we've applied it. This is looking at a very complex, essentially, it's called the pomegranate zircon, essentially a polycrystalline zircon in one of the Apollo 17 samples. And all of these bits of zircon in here have different orientations. And what we've been able to do with scanning ion imaging is take a series of analyses in here. Here are these little 70 by 70 rasters in different parts of this zircon to see how the ages might vary. Now, going back a little bit here, Bob Pigeon and co. back in 2007 reported an age difference between primary zone zircon of 4.3 billion years and a secondary CL dark amorphous zircon of about 4.2 billion years. So we already know what we should be seeing here. So this was a very good test case. So what we were able to do was take our ion images, and here's zirconium, uranium, lead, for 3 different areas. We did many. And what we can then do is use the images to define areas where we want to extract the age. And you can see that these areas can be very, very small in terms of how they relate to say a 20 square micrometer, and that's 20 square micrometer spot, not 20 micrometers. So some of these are very small areas. And we use that procedure that I just defined, and we tested it on Tomorrow 2 zircon. We get the correct age for Tomorrow 2 zircon, about 420 million years. So the method works. And then when we applied it to the lunar zircon, we found also that we get a very good match with Bob Pigeon's spot analyses. The primary zircon is giving us 4,300 million years, and the secondary zircon about 4,200 million years, with very acceptable uncertainties of just 10 million years. So we can do scanning ion imaging and obtain full lead uranium. So it's a very powerful technique. I'm going to skip these few slides for now, except this one. One advantage of, let me just go back, one advantage of being able to place very small areas near the edge of grains is that we can then use the ages in the context of defining diffusion profiles. So we can constrain the temperature generated during the impact that shattered this pomegranate zircon based on the change in age that we see and assuming some different cooling rates. It's not very accurate, but it's not too bad either. Okay, I'm going to skip this one, and I'm going to move on to the final part of my talk, which is lunar geochronology and lead isotope systematics. And this is something that we've been doing now for probably about 6 or 7 years in Stockholm. You may have seen the papers. It's a method that we developed and which is now being used. It was most recently used by the new samples from the Chang'e 5 mission in China to date lunar basalts.